So in this topic, we will discuss about the waves and electricity, the topics related to waves and electricity. The first was, and for Edexcel student, this is unit 2 for them. Like they have a separate exam for unit 1 and 2. So waves and electricity is unit 2 for them. And for Cambridge students, this is the same continuation of the topic. And I'm following the sequence of the syllabus. So as we were having the mechanics, the first part, the mechanics, material, motion, and now we have the waves and electricity. These are some learning objectives. First, how we define the term wave. So wave is actually, it's a mode of energy transfer. When we say it's a mode of energy transfer, it means it's a way by which energy can transfer from one place to another. And the transfer of energy does not mean the transfer of the particles, because some students get confused by the concept, the transfer of energy and the transfer of the particle. There's a difference between the transfer of energy and the transfer of particles. So some cases, yes, the particle do transfer, do move from one place to another, but wave is not the transfer of the particle. Wave is the transfer of energy by the vibration of the particles when the particles are moving. And the particles can vibrate parallel, the particles can vibrate perpendicular. So vibration of the particles can change, it can vary. So example, as you see a wave in the sea, the molecules, the disturbance of the molecules of the water as the molecules will go up and down. So it's not like the molecules of the water travel from one place to another. It's just the vibration or the energy transfer from one place to another. But what actually happened to the molecules of the water? The molecules of the water will only oscillate or vibrate up and down. But the energy transfer from one place to another. Then we can classify the waves into different categories. Some of the waves require particles to transfer energy. And some of the wave does not require particles to transfer energy. So we classify the wave in terms of the medium. So some of the waves require the particles to transfer the energy, and some of the wave does not require the particle. Even particles are there or not there, the energy will be transferred. So the types of the wave which require a medium to transfer energy, what we call them as a mechanical wave. And the type of the wave which does not require any medium to transfer the energy, we call them as electromagnetic wave. So mechanical wave, the best example of a mechanical wave is a sound. Sound is a mechanical wave. Why we say it's a mechanical wave? Like if you have the particles, the sound can transfer, like the energy can transfer. But if you don't have the particle, like if you have a vacuum, the energy cannot be transferred. So sound waves are mechanical waves. Means require a medium. But what about electromagnetic waves? The electromagnetic waves means it does not require a medium, or the wave can travel without, even medium is there or not there, but the wave can travel through a vacuum. So that kind of wave which travel through a vacuum, we call electromagnetic wave, such as light waves, radio waves, microwaves, infrared, X-rays, ultraviolet, visible. So all of these waves, the energy transfer without the need of the particle. If the particle is there or not there, but the energy will transfer. So first category of the wave is in terms of the medium, which can be electromagnetic or mechanical. Water waves, mechanical or electromagnetic? Water waves, electromagnetic or mechanical? Water waves, yeah, that's right, mechanical, because it requires a medium. Without the water is a medium, or particles of the water, the energy cannot be transferred. Same way, if I say radio waves, mechanical or electromagnetic? So radio waves are EM or electromagnetic because it does not require a medium. If it's a medium is there or not there, the energy will transfer. So the transfer of energy without a medium electromagnetic with a medium mechanical. Then the waves are classified into two categories. One is in terms of the vibration of the particles, the types of the waves. The types of the waves can be in terms of the vibration of the particles, how the particles are moving. But it's not like always the vibration of the particle, it's just a vibration. It can be vibration of the field as well. As later in this, we will discuss about electromagnetic waves. So we'll discuss how the field vibrate. So it can be in terms of the vibration, it can be a longitudinal or it can be a transverse. The longitudinal refers to if the vibration is parallel to the direction of the wave, and if the vibration is perpendicular to the direction of the wave, we call that as a transverse. So example, say these are the group of the particles and we produce a sound, like sound is traveling towards right. So what we observe the particles of the air or a medium are vibrating same as the direction in which the wave travel. So if the direction of the wave travel is same as the direction of the motion or opposite anti-parallel means 180. So what we call that as a longitudinal wave. But what if we observe the group of the particles and we observe the particles are vibrating up and down, but the energy transfer either towards right or left. So if the direction of the wave and the direction of the vibration is perpendicular or 90-degree, what we call that as transverse wave. So water waves, if you're observing the water, when the group of the particles are vibrating, these particles are moving up and down. And the energy, the wave transfer energy in this way. So as the direction of the particle and the direction of the wave is 90, we call the water waves are transverse. But when we produce like wave in a spring, so when we stretch or compress the spring, the energy transfer and the vibration of the particle is also same as the energy transfer. So we call that as a longitudinal. So all electromagnetic waves, whenever a wave is electromagnetic, it is always a transverse. And other examples like longitudinal waves, sound waves, wave in a spring, compressed spring, that these are longitudinal. So most of the waves we have transverse and very few of them are longitudinal. Is it clear the difference between a transverse and a longitudinal? Then there is also another category of the wave, which is in terms of, so as you can see here, the vibration is perpendicular to the direction and vibration is parallel to direction. So one is a longitudinal, another one is a transverse. Different examples are given, like example, sound waves or the seismic P waves, the pressure waves, which are longitudinal, all electromagnetic waves, and the seismic S waves are transverse. So we have the transverse in which the vibration is perpendicular. So as you can see here, the motion of the particles and the movement of the particles and the direction in which the wave travel both are 90-degree. So we call that as a perpendicular or transverse wave. So here the direction of the particles and the direction of the wave transverse 90 degrees. So that's also transverse. And when we talk about the longitudinal wave, in a longitudinal, the vibration is parallel. Then we have another is a continuous wave, like the difference between the continuous wave, the wave train, and the pulse. The term continuous wave means, like example, if you're not able to recognize the starting and the ending point of the wave, you will call that as a continuous wave. So for example, take a string, a wire, and hold one end of a wire and fix the other. And you disturb this end. So when you disturb this end, the vibration you will see like this. So, and continuously you're moving it. Like a skipping rope also you can take. So when you're using a skipping rope, or in this case, if you're not able to identify the start, like I cannot identify where the wave is starting and where, because I can say that this is can be a start of the wave, this could be an end of the wave, or this could be a start of the wave, or this could be the end of the wave. So if you're not able to recognize the start or the end of the wave, what we call this wave, we call that as a continuous wave. But what is the meaning of the wave train? The term wave train means like fixed number of the wave, a finite number of the wave, and we can, like continuous wave, we cannot identify the start or the end. Say you're using a mobile and this is representing a mobile tower which is sending the electromagnetic waves. So you cannot identify the start or the end of the wave. So what we call this, we call that as a continuous wave. But what is the meaning of the term wave train? The wave train means like when we have a finite number, when we have a finite number of the waves, and we can identify which point it is started and which point it end, what we call that as a wave train. So example, a person a person is standing at position A and another person is at position B. A person at A produced a sound and said sound waves are longitudinal, but I'm drawing a transverse wave. So this group of the wave travel from one place to another. So what we call that as a wave train. In a wave train, we can identify the start and the end of the train, and we have a finite number. So when we have a finite number, we call that as a wave train. But we have infinite number of the waves between, and we cannot identify the start or the end. We call that as a continuous wave. And what about the pulse? Pulse is like a wave train, but when we produce one signal or less than one signal, like one complete wave or less than one complete wave, one wave or less than one complete wave, what we call that as a wave pulse. So when we have too many waves, continuous wave, we cannot identify the start or the end. We have a wave train, which is a finite number of the waves, and wave pulse less than one wave. No, this is just an information additional thing related to the topic. You don't have to learn exam point of view. It's just a name given to the waves. We can have a continuous wave, we can have a wave train, or we can have a pulse. So that when we say a pulse, it means a short signal. When we say a train, it's more than one wave, but a finite number of waves. And when we say a continuous wave, it means there is no end or the start. It's just the wave travel from one place to another. Is it clear the difference between a continuous wave, wave train, and a pulse? Then, in terms of the position, there's also another category of the wave. So the types of the waves. In terms of the change in position, so when the wave change position from one place to another, so some of the waves travel from one place to another move from one place to another, we call them as a progressive wave. And some of the wave does not change their relative position to the surrounding, we call them as a standing wave. So progressive wave actually travel from one place to another. Like example, a person is there at position A and he shout and he call a person at position B. So actually what happened when the person at position A he shout, the wave actually travel from one place to another. So when the wave changes the position from one place to another, what we call this wave, we call that as a progressive wave. But if two people are holding the string like a skipping rope and they are vibrating the skipping rope and produce a pattern like this. So what does it happen? The waves are produced, but the are confined in the region. The wave cannot, like a wave is produced in a string or a wire, and that wave is confined in the region. Means that wave is within this region, a finite region. So what we call this type of wave, which does not actually change or move, like the wave is only produced in this region. That wave does not travel anywhere outside. So what we call this type of a wave, which is produced in a finite region, we call that as a standing wave. So a progressive wave is actually a wave which moves from one place to another, but a standing wave is a wave which is confined within the region. Is it clear? Then using a graph to describe the waves, different graphs are there. We can have a displacement distance graph. We can also have a displacement time graph. So we may have a displacement time graph. We have a displacement distance graph. If we have a displacement and distance graph, the vertical axis, the maximum distance from the mean position or the center position, what we call that as an amplitude. The maximum distance from the mean position is called amplitude. The distance between the two successive crests from one crest to another, or the distance between the two successive trough from one to another, if it's a time axis, what we call this, we call that as the period of the wave or a time period. But if we have a graph for a distance and displacement graph is there, if you have a distance and displacement graph, so the vertical axis, that is an amplitude because that's the maximum displacement from mean position. But the x-axis, the distance between the two successive crests or the two successive troughs, what we call this distance, we call that as a wavelength. So if it's a distance, displacement and distance graph, the horizontal distance between the two successive crests is a wavelength. But if it is a distance and time graph, displacement and time graph, the horizontal distance, like the length, is not the time, it's not the distance axis, it's a time axis, so it will be refers to a time period. Time period means time taken by wave. So crest is the top, like this is a crest, which is a top, this is also a crest. So between the two successive crests or between the two successive troughs, if it's a distance displacement graph, that represents the wavelength. No, the period and the wavelengths are not the same thing. Period means the time it takes to complete one vibration. So how much time the wave take to complete one oscillation or one vibration? If we have a time axis, x-axis a time axis and y-axis a displacement axis, this interval is called a period. But if we have a horizontal axis as a displacement distance covered by the wave, then the horizontal distance for a one complete wave is called a wavelength, which is denoted by lambda. So it depends on the axis. We might have a distance displacement graph, or we may have a displacement time graph. So if we have a displacement and distance graph, the distance between the peaks is a wavelength. The distance, maximum distance is amplitude, or the minimum distance means the maximum distance from mean position even above or below the mean position, that is amplitude. Is it clear till this point? Any question or doubt? Then we have a wave equation. The wave equation actually shows a relation between the speed, frequency, and the wavelength. How we define the term frequency? You have studied that. Frequency is number of vibration in 1 second. So, because when the wave is traveling from one place to another, the wave does not accelerate in the same medium. Like if a sound wave is traveling in through air, it does not accelerate. It has the same speed throughout the medium. If the medium change, yes, it does accelerate, but within the same medium, it does not accelerate. So if we say that speed is distance divided by time, the distance covered by the wave, if it is in terms of the wavelength, so we can say lambda. And what about the frequency? The frequency is a reciprocal of the time period. So if we simplify this, so in place of d, we can write lambda, and in place of 1 over t, we can write f. So it becomes v equals f lambda. This is called a wave equation, which is applicable for all kind of waves, where v is representing the speed at which the wave travels through a medium, lambda is representing the wavelength, the length of the wave, and frequency is representing the number of vibration in 1 second, or number of complete waves in 1 second. So v equals f lambda. Like the diagram below shows the displacement and time graph. The wavelength of a wave is 8 centimeter. We cannot measure the wavelength from this. Like if I say this is a wavelength, then it is wrong. Why it will be wrong? Because the displacement distance graph, we can only label the wavelength, but here we can only mention the time period. So in the question, state the amplitude. What is the amplitude of this wave? What is the amplitude of the wave? The amplitude is 2 millimeters. If we need the frequency, frequency is the reciprocal of the time period, that is one way. Or if we need the frequency, frequency is number of vibration per second. So it is the total number of the waves divided by total time. So how many waves are there? Both ways it is acceptable. So how many waves are there? This is one complete wave. This is a second complete wave, and then it's a half wave. So how many waves are there? 2.5 waves. And what is the interval for the 2.5 wave? 1.25. So 2.5 divided by 1.25 will get 2 hertz. That's the frequency. Or we can also use, first find the time period. Time period is time to complete one vibration. So the time period is 0.5 seconds. If I need the frequency, frequency is a reciprocal of the time period. So 1 divided by half. So the frequency will be 2 hertz. So it will give the same result. And if we need the speed of this wave, speed of the wave, speed is frequency multiplied by the wavelength. The frequency of the wave we worked out 2, and the wavelength is given in centimeter. So if you don't convert the unit, you will get the answer in centimeters per second. If you convert the unit into meters, then the answer will be in meters per second. So it will be 2 multiplied by 8. So 2 multiplied by 8 will make 16 centimeter per second, because the speed is frequency multiplied by the wavelength. So 2 vibrations per second, and the wavelength is equals to 8. So the total speed will be 2 multiplied by 8, which is 16 centimeters per second. Is it clear, this example? Another example, a radio station broadcasts on a wavelength of 250 meters. The speed of the radio waves is 3 exponent 8 meters per second. Calculate the frequency. So if you need a frequency, frequency will be the ratio between the speed and the wavelength. So when we divide 3 exponent 8 by 250, we get 1200 kilohertz. And the longitudinal waves, the particles are vibrating parallel. And the distance between, like the region where the particles are very close to each other, we call that as a compression. The particles have large spacing, we call that as a rarefaction. And the distance between the two successive compressions or two successive rarefaction, that is known as the wavelength. Now this is important, the phase of the wave. The phase of the wave is actually what we do. We classify the wave as a circular motion. Like we make a relation between a circular motion and the wave motion, and the angles which we represent in radian, we call them as a phase. It can be represented in degrees, but we can represent in usually represent in radian. Like example, if there's an object which is moving in a circular path, the object is at position A. When the object is at position B, how much the angle has changed? What is the change in angle from A to B? That is a quarter or 90 degrees. The angle has changed by 90 from A to B. Or in terms of radian, because 180 is pi radian, so it will be pi by 2. When the object moved from A to C, how much the angle has changed from A to C? So from A to C, the angle has changed by 180. Or I can say pi radian. But from A to B, the angle has changed by pi by 2 radian. If an object moved from position A to D, how much the angle has changed from A to D? 270, or in terms of radian, how much? Because pi radian is 180. So this will be 3 pi by 2, because 90 multiplied by 3 makes 270. So it's 3 pi by 2. Because like 90 degrees is pi by 2. 180 degrees equals to pi. So 270 is 270 degrees, 3 pi by 2. Because 90 multiplied by 3, 270. And when it returned back to the same position A, how much the angle has changed? If it returned back, the angle has changed by 360 or 2 pi. Now, what we can do, we can also categorize, we can also make the wave in terms of angle. Say we have the wave. So when we represent the wave in terms of the angle, we call that as a phase of the wave. Like example, this is point A, same. And this is point B. Point A to B, it's a quarter. So what is a quarter of the phase? Like if we say x-axis is an angle here. So from A to B, it's a quarter of the wave. So what will be the angle? The angle will be pi by 2 or 90 degrees. Then from A to C, because like in a circle, from A to C, the half circle is 180. So half of the wave, the angle will be pi or 180 degrees. Then 3 by 4 of the wave, the angle will be 270 or 3 pi by 2 or 270 degrees. And when there's a one complete wave, we return back to the same point. So we can say the angle or the phase is 360 or 2 pi radian. So when we make a relation between a circular motion and the wave motion, and we categorize the wave, parts of the wave in terms of the angle, what we call that as a phase of the wave. So actually, what is the meaning of the term phase of the wave? The phase of the wave is actually representing the mode at which the particles are vibrating or the positions of the vibration of the particles. Is it clear, the relation, the concept of the phase? Any question or doubt? So simple, the concept of the phase is actually representing the wave in terms of the angle. We call that as a phase of the wave. In the next session, we'll do more about the phase relation between the points and the phase difference between the wave.